start my days. Sun rays, I tap the phone. Coffee's on, I mow the lawn. Impressing Sean, so connected, so effective. I let it drop, clean it up. Heating smart, I do my part. Get in the car. Superstar, they're watching me. IoT, 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 IoT. I check my stock. What a shock. Buy some prawn. My oven's on. Coming home. Future zone. All for me. IoT, 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 IoT. Live like a Bosch, with many connectivity solutions for a smarter future. From Bosch.
Hello everyone and welcome to this event about coding the future of mobility. My name is Sead and I have the pleasure to guide you throughout the day together with Josie. Hi Josie.
Hi Sead, welcome.
Hi Josie, tell us what can we expect from today's event?
Yes, hello also from my side everybody and welcome in this historical Bosch garage. My name is Josie as mentioned and I hope you are curious as I am about our afternoon program. We have organized special expert talks with Martin, with Alexandra and Michael. And to keep the entertainment level high, we also have organized our in-house DJ, so stay tuned and be prepared for also some discussions with our hosts from the morning workshops. They are also in-house and so we are happy to welcome them here. So let's enjoy our afternoon.
Okay, that's very cool. So topic-wise, we are going to have some tech sessions about cybersecurity, software architecture, and machine learning. So looking very much forward to get some insights there. I want to say a big thank you to all of you around the world joining us online. A special thanks goes to the people joining us here at this in-person event here in the Bosch garage. And a special thanks also goes to Bosch for giving us the opportunity and possibility, first of all, to be here and host this event together, but also to get some insights behind the scenes of the future of the automotive industry. And with that said, I would also like to call on stage Peter, who is the General Engineering Manager at Bosch. Hi.
Hi. Hi, Peter.
Peter, thanks for having us today here.
Yeah. Thanks for giving us the opportunity. As we already talked today several times, we have a great success in front of us, a lot of things to become developed in future, new products, new business models, and a lot of very interesting guys needed.
Yeah, exactly. Peter, we had a very interesting interview in the morning, so for the ones who have not watched it, you can watch it on demand on WeAreDevelopers.com. And I mean, can you tell us a bit about the role of software developers in shaping the automotive industry of tomorrow?
Yeah, I think software developers are very important because without software, nothing will move. And software is a really right area. So we have software doing our development environment improvements, automation, doing some optimization, but also the coding of interesting parts which needs to be hand-coded or code-generated, up to developers who really design the functions in the cars, in every component, which are then finally used to make it much comfortable to drive or to have a sustainable car, to care for climate, everything that.
Yeah. There was one very interesting answer that you gave me today in the interview when I was asking you to give us 3 pieces of advice for software developers how to have a successful career. So you pointed out 3 things. What was that?
Yeah, I think the first was stay authentic. Yeah, you will for the next years cooperate with humans, not with robots. And usually everybody will cross again some years later, and based on your treatment of others, you will be treated. So really stay authentic, don't make pictures of you, stay authentic, be yourself, and then you do it right.
Okay. And the second one was, I think, stay flexible, right?
Yeah, staying flexible, I think, especially in our branch, it's changing a lot for a long time, and I invented the saying for myself that nothing is as stable than the change. And here we really should challenge everything which we did in the past, whether it's right now or whether it will be right in future. Changing everything, questioning everything is very important. If you want to be a front-end leader, a front-end or front-end developer, question everything and be prepared for the change.
And the third thing was work hard, I think, right?
Not only work hard, but don't wait that you get some offer and promise, then I will show power. It's the other direction. You first show power, and then you will get the award.
Okay.
Yeah?
So deserve the glory, basically, right?
Yeah.
Okay. And then one thing that I learned, which I found very interesting, you know, usually when you talk about Bosch, like outside of this garage or outside of the Bosch ecosystem, then you maybe might not think that it's actually a tech company, but it is, because it's not just, you know, the household products and tools and so on that you have and that you can enjoy at home, but it's actually really, you have 30K software developers all around the world working on smart devices, IoT connected systems, and it's also the largest automotive manufacturer in the world. That's basically also the topic of this event. So is it true that actually, you know, we are actually driving smartphones on wheels and it's more and more software development and not just mechanical engineering?
For sure. At the moment, there are some estimations that in 10 years, we will have about 10 times more software in a car than now. And if you take a view on what do we have now, in the typical car we have some 100 million lines of code. Yeah? So it will develop towards 1 billion lines of code in 10 years. And somebody needs to do that.
Wow, that's huge. Yeah, okay. Let's see who is going to do that. Peter, thanks for these nice words. Enjoy the event and see you later.
Thank you also. Thanks.
Thank you.
Thank you. So, for the ones who are joining us online, please don't forget to engage with us. You see a chat window beside the stream and a small button which is called Ask, so you can also ask questions. After each session, we will have a short Q&A session, so we can engage with the speakers and get the answers to our questions. Yes. One thing that we need to remind you.
Yes, it's as always, these events, we have a code of conduct, and please have a look at a short video for the code of conduct. Thank you.
Okay, so it actually means just be nice to each other and treat everyone with respect. And with that said, I would like to call our first speaker on stage. He holds a PhD from the Technical University in Vienna. Okay,
So.
good. Martin Schmiedecker, welcome here on stage. I just finished my introduction, so you are a true expert on cybersecurity, online privacy. You are working in this field and researching for many, many years. Maybe you can give us a short introduction of what are we going to hear from you today.
So I'm going to talk about the challenges of the future for automotive security. So I'm going to wrap up the hacks of the past, what has happened, what made it into the media, and what was impactful, and how we can defend against such things, basically.
Okay, great. I would say the stage is yours.
Yes.
Start the presentation and enjoy the first session.
Yes.
Hi. So my name is Martin. I work here in this very building and work on security topics, basically on development projects that are currently being prepared for production. I'm also part of the incident response team at Bosch Engineering, which means if one of our products is hacked in the field, so once the project is finished and it's hacked, I'm the one who is in charge of basically leading the investigation to figure out what is the impact for our customers and also for our end users. Said already said it, my background is in IT security. In my spare time, I also happen to do digital forensics, and basically all I learned is from Technical University of Vienna, so I'm kind of homegrown in this city. Who is Bosch Engineering? So Bosch Engineering is a subsidiary of the Bosch consortium. We employ around 3,000 people worldwide, and the headquarters, you can see it on this picture, is near Stuttgart in Germany. Basically 120 people work for Bosch Engineering here in Vienna, and we also have subsidiaries which specialize on specific engineering challenges, like, for example, commercial off-road vehicles, like things that keep the economy going but without actually moving people or goods on the street. What is Bosch Engineering usually involved with? So usually we do small, serious projects, things that do not scale in the millions, but rather have a few thousand vehicles or components or whatever it is we're building. So we are rather focused on the engineering part, and we adapt the Bosch products on the specific needs of our customers, which also means that usually our products can go very fast. So you can see it on the picture. From time to time, we have a track day where we invite our customers to actually drive the cars that we help build. On the other side, one of the projects that fascinated me very much in the past was an autonomous excavator. So instead of driving autonomously on the road with a car, the project here was to build an autonomous excavator which can do mining operations and work more or less around the clock, a few tons of an autonomous robot, more or less. Yeah, we also see one of the shuttles that we have been involved, so we're also involved in autonomous driving, and of course security is very, very important with each and every of those projects, because basically if someone is able to hijack an autonomous excavator or a driverless shuttle, then things can go haywire pretty quickly. So, brief recap of automotive security. Why am I employed by Bosch Engineering in the first place? Basically, cars have been driving around for, I don't know, 50, 70, maybe 100 years. But it only got interesting about 10 years ago when academia discovered that you can rather easily hack a car. So the IT infrastructure, the computers that were used back then, they had some form of security already, and hackers then shifted the focus towards less protected things like the car, more or less. And this is a particularly interesting paper that more or less started my journey into the automotive security world, because what they have been able to show, so this is an academic conference, it has been published at Usenix Security 2011, and what they were able to show is that there are so many different vectors to basically compromise the functionality of a car. My mind was just blown. So basically, you have tire pressure sensors within the tire that can send the air pressure, which is neat because if your tire is losing air pressure, this can become dangerous. And what they were able to show is that actually you could spoof the tire pressure sensor and send raw signals into the car, which are then interpreted by other components. So this is not a good thing to have if you're driving on the highway. They also showed, and this is also very fascinating for me, that they had an MP3 radio within the car, and you could, I don't know, plug in a CD and play your MP3 collections. Back in the days, there was no Spotify. You had Napster and all the different MP3 sharing services. And all you had to do was just burn it on a CD and plug it into the radio. However, the parser in the MP3 engine had a buffer overflow, which is like a very basic vulnerability. And it was basically possible to hijack the car or send raw car commands with a manipulated MP3 file. They also showed it that you could basically call the telematics unit, so you just need to figure out what the phone number is. You could call the car, more or less, and play this manipulated audio file, and you could remotely compromise the car over a phone line. And this was just, why is that possible? How can we prevent these things? Yeah, so that was my introduction into automotive security. We've come a very far way from back then, but there's also still a lot more to do. Then there was the infamous hack by Charlie Miller and Chris Walasek. They presented it at Black Hat 2015, and what they were able to show is that they could connect to specific cars while they were driving somewhere in the country. So they were hacking cars from the comfort of their couch at home. And basically the vulnerability here was that the connectivity units allowed incoming connections, so they had open ports, and within the same cellular network, it was basically possible to connect to the cars and manipulate its behavior. If you haven't seen this video on YouTube, I highly recommend it to watch it because it's quite scary. What they did is they took a reporter, they set him into one of those cars and sent him on the highway. And while he was on the highway, they've been able to activate the radio, activate air condition. They were able to activate the windshield wipers. And in the end, they could shut off the engine while he was driving. So that was kind of like a momentum in time where automotive security, well, shifted to the we need to do more section. Another ongoing threat to many car owners today is wireless car keys. So I have a wireless car key, and I like it because it's really convenient. However, there are specialized kits available that you can buy to basically extend the range of these key fobs. So the video on YouTube at the bottom demonstrates it. You can see the car in the driveway, and you see two people getting out. First one is having a black box in his hands, walking towards the door, because usually what you do when you come home is you drop your car keys and the regular keys, you drop them right next to the entrance. And so everything the thieves have to do is to get into range of the car key, extend the range to the car, and the car is tricked into believing, oh, my owner is standing right next to me. I need to unlock and allow to start the car. It was even in local media, so I think in 2018, Wien heute, so it's like a local news show, they showed that the police were able to arrest a gang of people that have been stealing luxury cars using this specific attack. And what has been very interesting is that they even showed these devices that have been used to extend the range of the car key. They look like makeshift, rather roughly boxes that basically allow the key to unlock and start the car. One of the problems in this particular settings is, well, the car could turn off the engine if it discovers that the key is no longer present. However, this is too dangerous for the people inside the car. So imagine you drive away, the car notifies you that, hey, you forgot your key, I will shut down. This is not a good situation while driving to shut off the engine. So this is why it doesn't happen. And there are currently projects ongoing, also at Bosch and also worldwide, to basically prevent these attacks with modern technology. What's also interesting is the different car manufacturers proposed countermeasures. So one of the countermeasures when such an theft occurs is, well, you have to put your key in a tin can to block the radiation. I won't do that because I cannot simply drop it off next to my door. The other countermeasure, so to say, is to have a PIN code. So instead of turning the car key, you enter a PIN code into your car. But if I buy a car which is like worth 50,000 euro, I never will, but let's assume I am able to buy a car that is worth 50,000 euro, then I wouldn't like to have to enter a PIN code every time I would like to drive away. Yeah, just last year, another very, very impressive hack happened. It also was in the media and was broadcasted widely, was a Tesla hack. Basically, this guy in the video, Leonard Wouters, he's a student from University of Leuven, and what he has been able to pull off was really, really astonishing. So he found out that for specific key fobs in the Tesla X, you could basically remotely acquire an unlock token, walk then to the car, unlock the car, and then get into the car and train a new key. So basically it was it left no traces. It wasn't a regular snatch and grab where you are mugged and give me your car key, but rather you have to be close to the owner of the car key. You can get the token and then drive away with a car and, I don't know, do whatever people do when they are stealing a car. And the technical details in this particular hack are really, really astonishing. It's a piece of art, more or less. And also another hack still ongoing. So this brings us to today's. Just 2 months ago, the German ADAC published a story where they have been able to manipulate the Kilometerstand, or the odometer, from modern cars. So when you buy a used car, you usually check, okay, has it been driven much or rather less? And you do that by looking at the odometer and see, okay, that's 550,000 kilometers. Pooh, I probably won't gonna buy that car. But they found that with regular tools that you can buy online, you can manipulate the odometer and either increase it or usually just decrease it, which is, of course, a bad thing. And also, of course, it's illegal, but people might do it anyway. So you might think, what is the motivation of an attacker? Why would they like to hack cars? Well, for the first part, it's about curiosity. People would like to understand and know, how does a car work? It's a complex thing. It's a smartphone on wheels, or in fact, multiple smartphones. So they would like to understand how it works and how it can be extended with customized functionality. Another factor is, you can read it again and again in the news, tractor hacking, which is very popular for farmers because if their tractor breaks down, they cannot work with it. They are relying on the tractor to work. And if it breaks down, they either have to bring in the tractor to the next dealer, which is sometimes a few hundred kilometers away, or they have to get a service agent come to their place. And I don't know, they don't grow on trees, these service agents, so the tractor is not usable for some time, which is bad. So that's why they would like to repair the tractor themselves with software, and is kind of a fight between the tractor vendors and OEMs versus the farmers, because the farmers relying on them and the manufacturers really would like to have it in their hands to service these vehicles. One of the best challenges against car hacking, or one of the best countermeasures, is that if you would like to hack a car, you actually have to have a car. So if you would like to hack a modern, I don't know, 100,000 euro car, whatever brand it is, the first thing you need is you have to have this 100,000 euro car. And no hacker has this much money available. That's simply, right now, the best countermeasure against car hacking on a large scale. And this is becoming less and less relevant for modern cars because they are connected, they have a backend, they can be remotely contacted, and so forth. So we need to do better than just say, okay, the best countermeasure is to make the price really, really expensive. So what does it mean? What is the consequence for today's developers and also developers of the future? How can this work? Basically, one of the biggest problems that the entire automotive industry, in my point of view, is facing right now is complexity. So you have multiple components, very powerful components. They would like to communicate with each other, do it in a secure manner, and this is where the problem starts. You have an increasing complexity, which makes it really hard to secure components or vehicles on a large scale. But that's not the end of it. You have supply chain hacks. Basically, what happened to SolarWinds, a company in the US that was selling remote administrative software, what they have been facing was that they have been hacked. Someone added malicious functionality to their product, and with that functionality, they were afterwards the attacker empowered to connect to hundreds and hundreds of companies to basically compromise their security. You have ransomware. This is basically where the SolarWinds hack led into, that actually right now it's a business model to encrypt data and demand a ransom to get the key back. And this works. It works surprisingly well. And people again and again are troubled with the fact that their data has been encrypted, entire companies are breached, and their data is encrypted. And this can lead to all kinds of problems, downtimes, production loss, whatever it is, you name it. Once your IT system that you're relying on is no longer working properly, this will lead to plenty and plenty of pain. For a car, what's also troublesome is connectivity. So a modern car, if you buy it today, has 2 to 3 SIM cards in it. The number of this is going to probably increase in the future. So these cars are online at will and can do internet-related tasks and services on demand. You have wireless interfaces, so the car not only uses 3G, LTE or 5G to connect to some backend, it also has Wi-Fi, it has Bluetooth, it has probably multiple Bluetooth or Wi-Fis, and all these are increasing the attack surface of a car. So if I would like to hack a car, first thing I test is how is this thing broadcasting and how can I abuse this to my advantage. Also, you have a rather unfriendly environment because the car is sold as a whole, and whoever buys the car has full physical access. Usually for IT security, physical access means game over because you could change anything to the underlying components. And the same is true for cars. If I would like to protect a car, the best thing to do is to pour it into a block of concrete, because then it's secure, but then it's no longer usable. And yeah, plenty and plenty of problems. Each of those problems alone could be worth a project employing multiple experts for years to come. Another problem, or another feature, so to say, is that software is everywhere. Every component in a car runs software. What you can see on the right here is my car. It's an entirely softwareless car. It's a Land Rover from the 60s, and there's not a single component in there that runs any form of code. And of course, these cars existed, but they vanished to exist for a reason, because software now runs everything. So regardless of your expertise in software development, there is a place in the modern mobility ecosystem where you can basically contribute to make things work better, safer, secure, whatever it is. And the entire component range from, you have microcontrollers, these microcontrollers have a hardware security module built in, ranging to telematics units, fleet management, whatever it is, software is everywhere. And what the past has shown us again and again is that if you fail to secure software in time, it will come back to haunt you. So if security isn't built in from the very first moment of software development, you will going to have a hard time adding it at a later point in time. And of course, autonomous driving. Everybody's talking about autonomous driving. People would love to drive autonomously with their car to work or back home. But there is just no way this isn't done by software. So the software is controlling us meat people in a 2-ton metal thing. And of course, the challenge is to basically ensure that these metal boxes do not kill the meat people inside of themselves. Yeah, autonomous driving is also incredibly difficult because the software decides how to react. In the picture, you can see the Ariane 5, which is basically a powerful rocket that crashed in spectacular way on the first flight, and the problem was an integer overflow. So he had a counter, that counter was counting upwards, and in the end, the integer overflowed. This wasn't caught by software, and the entire software calculation model got out of their expected behavior, so it basically killed itself, the rocket. Same is true for autonomous driving. You have software that decides much faster than a human can intervene. And this can lead to all kinds of wonderful things, but of course it can also lead to plenty of problems if the software decides to do something prior to the human even realizing what is going to happen. The software will also only increase. So a modern car has a multitude of sensors built in them, ranging from camera systems, tens of cameras. You have laser sensors, so-called LiDARs. You have radar. You have vehicular communication. Cars can probably in the near future talk to each other on the highway, but instead of, hey, what's going on, they're going to discuss driving conditions and whether or not it's a good idea to drive 180 on the highway. And this can, again, lead to unfortunate situation where humans can be harmed simply by one of the cars saying things that aren't untrue and basically catching the other cars out of their comfort zone. Another project which is currently developed is smartphone as a car key. So I showed you the relay attack where people artificially extend the range of their car key. There is an international collaboration effort ongoing to basically replace these insecure keys with a thing that everyone carries around with them. So a smartphone has many, many advantages compared to these key fobs in power of calculation, battery lifetime, interfaces, and so forth. So in the future, chances are very good that we will unlock the car seamlessly, but instead of a car key, we will use a smartphone. Yeah, and of course, this will be more secure. We can nowadays pay with a smartphone, so why not just unlock a car with it as well? Yeah. Also, it leads to a whole range of new services. So just imagine you are arriving on a business trip, you're getting out of the plane, and you have to find the rental company because you're taking a car and driving on. In the future, it might be just the case you get an email, you get a notification, hey, your car is ready. We already stored the car key in your phone. You can find the car here. And this is as convenient as it can get. And I see great potential in this technology because it's safer. It's probably not safer, but it's more secure compared to the regular car key. And there is upcoming legislation. So this is also interesting. Remember the hack back in 2011? The international consortia have derived international standards that will be enacted in the future. So one of these standards is the ISO standard 21434. Basically, this standard requires manufacturer of components or cars to have a process in place to make a secure component, and this can be audited. And the same thing is true for type approval or vehicle approval. So if you are a manufacturer of the car, in the end you would like to have one approving authority that says, okay, this car is good to go. And this is the UNECE, which derives the norms for what is required for releasing this car to the public. And one of those legislative items will now be that the manufacturer has to have a plan or a process in place to ensure that the vehicle is secure and stays secure over the lifetime, and that the manufacturer can react to security issues in components or logical vulnerabilities. Whatever it is, this requires the manufacturer to enact a plan that can be checked. What's also interesting, in particular for you as a developer, one of the things in security is that you have to stay on top of the game all the time. This is true for everything related to programming, but also for security. Each and every month at least, probably even week, you can read of new vulnerabilities that are discovered, potential impact on end users, and so forth. And I listed here some of the resources that I check regularly to stay up to date, to know what is the current hot topic in security that needs to be addressed in development projects. One of the things I would like to point out is the Automotive Security Research Group, or called ASRG. It's basically a loosely coupled group of interest worldwide. They have a weekly stream for interesting talks and discussions happening on YouTube, totally COVID safe. So if you would like to get into automotive security, this is probably the one best thing to look out to stay up to date and informed. Of course, there are conferences, there are papers, there's many resources available online which you can query to find out what is currently the biggest challenge in automotive security. With that, I hope you enjoyed my short journey about the automotive security and why this will be important for the future mobility. And I hope you have some questions that I'd be happy to answer. Thank you.
So thank you very much for these interesting insights.
Yes,
Thanks.
thank you.
So let's see if we have some questions from the audience. Just raise your hand and you will get a mic. So if there is any question, otherwise I'll go on with the questions from the online participants. No questions here so far. Okay, just raise your hand later. So we have one question. It's maybe not super technical, but I think it's also something that is really a lot discussed also in the media. Robert is asking an autonomous driving related question. In case of a car accident, when the car was driving itself, who will be responsible?
That's a tricky question because basically it could be a mixture of responsibilities. To be honest, I have no answer to that question. It will be derived by the legislation, so I assume that there will be laws or terms of conditions for car insurances to figure that out. But in the end, it's probably the car's fault, which means it's the owner, it's the manufacturer, as well as the company deriving the software for driving autonomously. So, yeah, could be anyone.
Yeah, it's indeed tricky. I think nobody has an answer to that one so far. But when we talk about legislation, I mean, when we develop autonomous cars already today, we also know that, as you say, like legislation is still to come. So what effect has this for the development of these systems? Because you basically have to do something and you don't know like what's the future, do you need to change it and so on?
Also a very good question. So basically for autonomous driving, you have to anticipate all the absurdities that can happen in real life and anticipate a reaction to that. And whatever it is, it has to be caught in software. Software has to deal with that and has to do in a way that is basically safe and secure for everyone around them.
Okay. Markus is asking, are the systems for security standardized across the industry, or is everyone building its own systems?
So from Bosch perspective, the building blocks are more or less the same in the entire industry. So you have hardware components that do security calculations. You have functional components for encryption, for authentication, for verification. All these things are rather standard pieces that can be found just as they are in an IT product, in a smartphone, whatever it is. It's just that the details are always developed by the manufacturer. So only the manufacturer knows how to secure this vehicle against the anticipated threats, and how this can be done is using standard blocks like encryption, authentication, things like that.
Okay, then let's see, we have some more questions here. Kerstin is asking, cars will be part of the shared economy, so how to prevent people from hacking the car hardware from the inside when everyone has access to it?
Yeah, good question. So hacking from the inside is basically, it can be prevented by verifying software before it is started. So before you run a particular piece of software, the component can verify this is legitimate software. I have the authority to run this, and if it is manipulated, it can stop working. The problem with this is that the hardware components that support this, they are not on the cheap end. So they are on the more expensive range of what they can support. They need to have a hardware trust anchor. The software needs to be developed to work in that particular condition. So basically, it depends on the manufacturer to derive what are the biggest threats and to protect against them. So even though we have all the things we need, we could protect the entire car against manipulating software. It's just not yet economically feasible. It's just too expensive.
Then Robert has again a question, and he's interested in the technologies behind all of this, what we are discussing here. So what kind of programming languages, systems, tools, and so on are used?
So basically, most of the components are very close to the hardware. So they're using C or models derived in MATLAB. They don't even run a dedicated operating system, but they have dedicated firmware, which is written specifically and customized to this component. Everything C-related or assembler-based is good because it's fast, and these components need to react very, very fast.
Okay, thank you. Then, are you ready for a couple more?
Yes.
Okay.
Anything.
Rafael is asking, if cars have all backend and data is gathered by producers, are there AI, artificial intelligence or machine learning solutions to detect hacking?
So artificial intelligence is kind of hyped because they can detect similar things. So if you have a face, it's easy to train artificial intelligence to detect the same face again and again. What is really hard is to detect things that are outside of the norm. So even though artificial intelligence is a hot topic, I don't see it yet for security, mostly because, yeah, not sure how to say it, but basically it's easy to detect known things, but it's very hard to react to unknown things.
Yeah.
So, yeah, it will take a few more years and millions in marketing budget to make AI for security, I think.
Okay.
My personal opinion.
Our next speaker, Alex, is, I think, doing some machine learning live coding on stage, so maybe she can help us out with that a bit. Yeah, and let's go to the last question. Luis is asking, if some security measures are going to be centralized on a central server, could something happen like with Facebook 2 days ago? I mean, apparently it was not a hack or a security issue. Apparently it was a technical issue, but could be.
The answer is, as always, it depends. So, of course, Facebook knows how to run a global network of servers, but humans are bound to repeat the failures of the past. So it might be the case that 5-10 years from now, a car isn't driving because it's not able to contact the backend. It's unable to refresh a cryptographic key. The certificate is expired. So everything that we see on the modern web today will be part of the car within the next 5 to 10 years. So yes, it will be the case that security will prevent a car from driving.
Okay, so if Elon Musk accidentally touches the red button when he stands up in the morning, all Tesla stop. That can happen, actually. Yeah, do we have some questions from the audience here in Vienna? Anyone? So here is a question. Just a second.
So this is more of a philosophical question, but we heard today that in 10 years there's going to be 10 times more software in the car than now, and every day I read about like a ransomware attack or something. So why don't we all just drive the Land Rovers from the 1960s? I mean, wouldn't that be a lot safer?
Yes, it would be more secure from ransom perspective, but it wouldn't be economical anymore. So it's just easier to derive one component and configure it in software than to have 50 different components for the 50 different variations of a car. It might be the case that we fall back to these mechanical cars at a later point in time, but right now the trend is in the opposite direction.
Okay, are there more questions from the audience here, from Vienna? No. So, good, yeah, then I would say thank you so much.
Thank you, Martin.
You're welcome.
Thank you. So, our first expert is done, and I have the honor to introduce our second one, and she's a true wunderkind, if I can say so. She holds already a bachelor degree from the Technical University in Dublin with already 19 years. Worked already with a lot of programs like on the MIT, at CERN, with IBM, and already a lot of awards with quantum computing, machine learning, and I'm very proud to have here Alexandra Wildherr. Bitte schön. Please. So welcome on stage. The stage is yours.
Hi,
We're
Alex.
Excited.
Hello.
Hi.
Alex, have fun
Thank you.
and show us how to get started with machine learning, right?
Yes,
Perfect.
we will listen. Thank you.
Okay, so I need 1 second for my laptop and then I'm with you guys. So. The HDMI. Yeah, I know. Perfect. Thanks.
So, are we ready now? Great. So, welcome back after a short break. I think the Technic needed also, after 2 years of event break, a few minutes to get warm. So, again, Alexandra, the stage is yours, and we are expecting something from you. Thank you.
Thank you. Hello, everybody. Thank you. Half of this applause goes to the tech team for helping me figure out how my HDMI connects to the presentation mode, so thank you so much. What I brought today is this bit of automotive expertise. I'm actually not an automotive person, I'm more of a chemistry person. This piece comes from an internship or a line workshop that I did in the summer in the automotive industry. But I will still talk about automotive and machine learning today because chemistry and machine learning are actually quite related. And the cool thing is, if we think about artificial intelligence and we go back to the beginnings, the first models of artificial intelligence that were built by researchers that tried to figure out how to model a brain cell. So they actually used the machine to build a model and to build electric circuits that make a model of a brain cell so that they can better understand the brain cell in a laboratory without having to dissect human brains all the time. But then over time, they found out that it actually is kind of cool because these neural networks do logic that can be helpful for us humans in various tasks. And even if we don't understand all the networks yet, they can also help us understand things that we also don't understand yet. And it's like a bit of a box approach. First, it started to learn about the organization of our cells in the brain, but then this organizational stuff of logic components in our brain came into something and grew into something that makes us think, can machines think as well? Like, can we connect components of machine in a way like we compare neurons in the brain that gives us the ability to think? And the first things that get into this direction were tree-like structures and tree-like algorithms that try to minimize and maximize things, for example, chess, or that try to understand perception of the human. And also they try to understand how different graph networks work. And after that, then in 1986, something really cool happened because backpropagation was invented. And backpropagation then helped these algorithms to reiterate over themselves and to improve themselves by doing more and more cycles of a repetitive behavior, and by doing this, improving with mathematical functions on their own structure. Because in machine learning, structure is very important because the structure is a key component and part of the algorithm. So a lot of different structures and components were then invented after the backpropagation that then used it. But we not only need the structure of the algorithm, we also need the data. And so I think in 2009 something very cool happened, which was called ImageNet, a data set with everyday objects that you can access and download for free, and it's very versatile and very, very large. And in 2012, the ImageNet competitions were held, and one really cool competitor called AlexNet was very good out-competing the others. And what they did was they switched from using CPUs to GPUs, so graphics cards. And by using this, they multiplied and accelerated machine learning. And at that point, the industry got very curious. And also Google started to develop their own processing units called TensorFlow processing units, TPUs, to even be better at all. And then in 2016, we got not only better in industrial applications, but also in games. And then in 2020, we got very good in chemistry, which we'll touch later. So you see, it's a very dynamic and versatile field, machine learning. And that is why a definition of what machine learning is very, very hard. I just want like a little bit of a hand pull, like from I don't know anything about machine learning to developed all the algorithms myself. Like, where do you see yourself between 0 and 100? Okay, a little bit? Okay, that's cool. So I want to talk about what machine learning is and what it isn't. So machine learning is a subset of artificial intelligence. Artificial intelligence, like we saw earlier, is, for example, an artificial intelligent car is not only the machine learning part, which is the processing part, but also like the robotics, the sensorics, and all the other things. And instead of machine learning, there's this deep learning component. And deep learning is kind of really trying to configure a brain-like structure, where machine learning uses statistics to find patterns in data. So we try to have an input, use statistics in a model, and then output something. This is what we use for machine learning. And depending on the data we have and the task we have on hand, we need different kinds of statistics. So we can have linear models, where we try to find a common attribute amongst the data set, or we can have different parts, like classes, in our data sets, and then we try to do something where we use classification. So when we try to have something with similarities, we use a regression model, where we can predict a numerical value most of the time. And if we want to have different classes, we use a classification algorithm model, where we predict correct classes. And then we can also say, okay, we want only 2 classes, so a yes or no thing. This is binary classification. Or we want multiple classes, for example, different brands of cars that are seen in images, then it's multi-class classification. And on these 2 very basic schemes, we can add clustering, for example, where we find different attributes in a vector space, and also support vector machines, where we try to find the boundaries between different classes in our data sets. And then a really cool thing is decision trees and random forests. A random forest is just a collection of decision trees that do voting together. And a decision tree in the end is trained to ask the right questions. And I want to do something with decision trees on you today. So we will try to find out if we can predict CO2 emission data in a regression model with a decision tree today, with a random forest. So give me a second to start everything up, because my laptop at the beginning didn't want to start everything up. So I need to do this now with you together. So I prepared a little bit, and I found a data set that is very cool and has something to do with automotive. So it's for CO2 emissions of cars. And we can find it on Kaggle. And Kaggle is a very cool website. There are also competitions and data sets, and everything has to do with machine learning here. It's a very cool place. And you can just download this thing here, and I saved it on my laptop. And first, we need to import some modules. Pandas is especially for grabbing data sets into Python. And then we need to understand the data set. So in every kind of machine learning pathline, what we first need is we first need to have a data set. Then we need to find out which model we want to use. In the third step, we kind of combine the model and the data set while we do the training. And then in the fourth step, we try to improve our trained model to make it ready. And then in the fifth step, we have the production, where we have the model that's ready, and we can just send it and use it to do our prediction tasks. So we try to understand the data set. So for example, how many entries do we have in the data set? How many features does each data set have? And how many columns do we have that are our label? In our case, when we look at this, we see that we have 7,000 entries, so 7,000 different cars, and 12 different features. And we have these different features, for example, make, model, vehicle class, and what's important for us is this one, the CO2 emissions. So this is our label. All of these things here in the beginning are our features that all contribute to the final output, the CO2 emissions. And we can also see statistical things when we use describe on a pandas data frame, which is a very useful command. And then we can also print the first things. So for example, we see Acura, ELX, and then we see vehicle class, engine size, cylinders, etc. This is only the data preparation part. And now, when we have all this data, we need to split it like a teacher. So we are not a teacher for our model. So we don't want all the data to go into the model while we do training, because then it would be like giving students the test prior to the test state. That's not very good. So we need to split the data first into the labels, so the correct answers, and we also need to hold a little bit back for a test afterwards. So we have this, and then we try to put out this here. So I did nothing else but taking all of the features and splitting them from the CO2 emissions. So I have the CO2 emissions now separately stored in my labels, in my CO2 labels. And we see the other thing that I did is to get the dummies. And get dummies just means that we kind of converted all of the text things into numerical values, because statistics only works with numerical values, not with text data. But the problem is that we get many, many, many columns if we convert everything into text data, into numerical data from all the text data. So I say, what's probably not the least important feature? The least important feature is probably the model vehicle class. And that's also a very good thing. If you're training a model, try to cut down on the number of features. So I cut down on the model number of features, and now I have less features, but with more condensed information. OK, now we train the model. So this is just splitting training and validation data sets. And now I use the scikit-learn model, and I use a random forest regressor. So I use a random forest model with a regression feature. So I want a numerical output in the end. So this is now trained. This is all my hyperparameters that I can or could be improving on. And then I can make predictions. So now, from all the things that I hold back for the test, I pass them on, and I get a predicted data frame. And we see here that those are the predicted CO2 values, and those are the actual CO2 values. And we see there's some kind of error in there, but some are quite close. And if we use the error and accuracy scores, we see that we get to an accuracy of about 98% overall. Of course, we can clean this up for higher and lower values, etc. But it's actually quite good for an easy model. And this is everything, just code and code and code. Wait 1 second. We need to find out an error here. What's the problem? Wait, maybe it still worked. Yeah. No, it didn't. So let's try again. OK, now it worked. And now we can even see our tree here. So this is one of the decision trees that I put into my random forest. And we can zoom in. And we see that we get different questions that the model asks. For example, for feature X, the fourth feature, is it lower than 10.95? And so on. And we can then find out what are the most important variables were. So from all the feature inputs that we gave, so from all the things here at the top that I showed you, all the features here, everything until the CO2 emissions, and we put out the model and the vehicle class. We found out that the combined fuel combustion is very important for the CO2 emissions, and that the engine size, for example, is not important. And we see this here, importance and the different variables. So this is how we can use a model or train a model very easily. And how it learns is actually by taking the input, using statistics, and producing some trained model output. And we have 3 different types of doing this, either in a supervised way. So we give it the X and the Y features, like I did at the moment, where I put in the features as well as the CO2 predictions that we had in our data set. Or we could do it unsupervised, so I could only give the model different insights, for example, only pictures, and the model should find out itself what the pictures are similar in. Or I can do reinforcement learning. And reinforcement learning is like being in an environment, getting feedback. And for me, it is like getting my driving license. I only got my driving license like 1 month ago. And at the beginning, it was like I had really no idea what I was doing when I was in the car. But by the feedback from other honking drivers and by the feedback from my driving instructor, I got better. And that day, like after 1 month, I was quite confident with my driving skills. And now I'm very safe driving on the streets. And this is what machine learning is. It's iterating the process, getting better, and doing so on. And deep learning is just a subset, as I already mentioned, and where we try to really model the brain structure. So here we have the different neurons, which we model as values in matrices, and we also have weights, and weights are connections between neurons. And by the correct matrix multiplications, we can map a whole neural network in there. This one is not very deep, and we can model trained by weight optimizations. So what we do is, with an iterative process, even in a small model, we try to make it figure out which connections are important and which aren't, like neurons in the brain. Neurons that fire together, wire together, the whole saying. And then when we have the trained model, we can put our data in and get an activation according to probability. We see this is higher activated than the other one, so this will be our output, and this is our produced prediction. A deep neural network now has multiple layers and even activation functions in between. So not even if a neuron may be connected to other neurons, it doesn't mean that it necessarily has to fire. Some neurons in our brain, they're also activated by other neurons, but they don't fire. So the activation potential is not high enough in this case. And this is why deep neural networks produce something like very unlinear. And unlinearity is hard to predict, but it's good to model our real world. And that's why we think deep neural networks are very good at doing stuff. For example, this is a very crucial neural network with a lot of layers. You see, it's a 34-layer residual. So a residual neural network says just that we don't use every layer and pass it to the next layer, but we sometimes also jump over other layers. And this helps by distributing information, distributing the training. And you can use this especially because it's convoluted, and convoluted means that we take pixels as inputs, push them down, and then in the end push them up again. And this means that we can use it for image classification. And this is maybe important if we want to start with machine learning. There will be problems that arise. And this is just a small subset of problems that I found come often. We have overfitting and we have underfitting. Overfitting is when a model is too complex and the dataset is too small. Underfitting is when the model is too simple and the dataset is too big. In essence, if you overfit, then your model outsmarts the dataset. So your model is smarter than the dataset, and therefore it can abstract everything perfectly, and it learns everything by heart. But you cannot generalize in the end. If you underfit, then you give the model too much to do, and it cannot really meet up to the expectations. So try to figure out how you can make your data more accessible, or if you can use another model. And if it's not representative what you're programming, I mean, if you try to do it in the real world, which is especially important in the automotive industry, then there could be a bias in the training data. For example, you could only have a subset of the real world data, or you're sampled always in the same cities, etc. And then, if you have bad accuracy, either it's a programming issue, so I did bad programming, or I put in bad data, or I chose the wrong model. I have a really fun example for bad data quality. So we can use a framework that is built on PyTorch called FastAI. And the other thing is TensorFlow, so we can use those two frameworks very well for doing deep learning. And we just go quickly over it, because I don't have enormous amounts of time. But FastAI is a framework where it can help to do image classification. And you can use it with neural networks and everything else, and there are a lot of architectures built in there already. So I will not run through it, because I don't know how much time it will take, because I can't train it on my laptop. But the thing is, what I did is I just got onto Google, and I Googled some kind of pictures. So for example, something that's related to cars would be a tree, or like would be maybe traffic jam. And the fun thing is, if you want to have noisy datasets, just go onto the Google image search. This one is actually quite neat. Scroll down a little bit, and then you can download the whole page, traffic jam research. And when you do this, and you will not only get the HTML format for the whole page, but if you have images there, there will also be a lot of images downloaded. But you see, not everything, for example, this picture here is not a traffic jam in the end. So there is noise in our data. And this is good to predict noise. So I did this for a few different categories that I think are important in traffic predictions, and I stored them into the traffic dataset. So accident, intersection, junction. I put two things that are very similar, intersection and junction in, so we can see if there's bias in the dataset. Then models, people, stop sign, and tree. Okay. So I've downloaded this, and I've put out these different classes. And now I gave the model the data from my folders, which are different labels, and I told them to normalize them so that they can fit into my architecture of the neural network. And you see that these are just normal pictures that may be used for training, and some of them are, for example, accident. It's not really the cool best picture for an accident, but let's see how the model is doing. So we can then iterate over the process, and I only did 4 training iterations because I saw that the error rate is not really getting significantly better. And it's very hard to train something, a small model, because I wanted to train it on my laptop, so I don't have to connect to the Wi-Fi here and do it again. But we see I have an error rate of about 25%, which is not really good. But we could improve the training by looking at the learning rates. And the learning rate is essentially how fast you want the model to improve. So in the end, what you're trying to do is with the model, with each process, you try to minimize an error function or a loss function. And if you go faster or go bigger steps, you maybe step over the most important point. And if you go too slow, you maybe not reach the most important point. So by finding the optimal learning rate, where the loss is decreasing the fastest, for example, in this area, I could improve the model. And then I saved it and exported it, because I can then use it. And this is also a very important plot for a confusion matrix. So you can look at which would be the actual values and what were your predicted values. And in my case, my model did very bad to look at, if you look at intersection and junction. Normally, it should be only the diagonal. What we see here, that my model always confuses intersection and junction. And this is kind of expected, because we say intersection and junctions as kind of similar words for the same thing in the traffic accident. So I see that's actually not so good. So maybe I can put them together afterwards in my dataset, or train a model again to maybe differentiate those things better, but maybe we even couldn't find really a differentiation. And we can see that when we plot all the top losses, some of them are very strange. Like, I would not have recognized this as a tree or an accident myself either. This is neither an accident nor a junction. I don't know, maybe the taste of the food was very bad and it's an accident, but I don't get it. And we can also see where the model kind of found the different parts. So this one is kind of really unambiguous. You can not really see that the model found anything, but here you see that it really looked at the curves and the edges. You always see that the curves and the edges were the parts where the model most importantly identified different things. And this is where recurrent neural networks are very good at. Convolutional neural networks are very good at. They are very good at finding different paths in networks. So they're very good at finding different shapes in networks or in pictures. So this is why we use them for images and vision. And the recurrent neural networks ones, or long and short-term memory, are those that feed back onto themselves. And you can use them for language, because language is dependent on the word before it. So if I have a sentence and I need to understand the sentence, I don't only need to understand one pixel or one word. I need to understand the word before it as well to get the context. And there's also transformers, which are kind of a recurrent neural network with other things in there as well. And transformers was published, I think, in 2019 or even before, and are very, very good at the moment in doing language tasks. Okay, last thing before I write myself into words all the time is the autoencoder. And the autoencoder is a neural network structure. We have a lot of input neurons and also a lot of output neurons. But in between, you try to condense the information down to the most vital pieces so that you can build up from this. And this is important to extract the most important and valuable parts. And it's used in a lot of algorithms. I've not worked so much with autoencoders myself, only I haven't programmed anything. So only worked with pre-coded stuff. But what I really want to show here is the crash course from machine learning from Google, which I also enjoyed. It is quite cool. And there are also rules for machine learning that are also by Google, which are also quite interesting to look at. And now the interesting part, machine learning automotive. I hope I didn't confuse it too much with all the vocabulary in the beginning, because for me it was also quite confusing. I want to add one more word here that's vocabulary-wise, which is image segmentation. So we saw that there's classification and there's regression, so different classes or one value as a numerical prediction. But what image segmentation does is it not labels one picture as, okay, this is a car picture, but it tries to find the different parts in the picture where, for example, a tree is, different parts where the people are, and different parts where the cars are, or where the traffic or the houses are. And this is, for example, how cars look at the world. But cars cannot look at the world only by a computer, so not only machine learning is important, but especially sensor technology is important. The security aspect is important. The whole artificial intelligence part is important. And I saw that Bosch has 6 really important or big topics that they want to understand better and that they are doing investigation on. So we saw that they are doing stuff with rich and explainable deep learning, then also reinforcement learning. Reinforcement learning, as I said, was the start where you have an environment and you get the feedback. And we also have multi-dynamic multi-agent planning. So I think those are really cool things, and I would love to learn more about that. But as I said, I use it mostly for chemistry. The automotive industry, what I found by reading papers, because if you do chemistry, if you do science, you're good at reading papers, it is very good in, or often used in maintenance, so for seeing if there are any kind of predictors that the quality of a product is bad, or predicting predictors that there is maintenance needed, so time series stuff. Then also in marketing and sensor signal processing, of course, because the whole thing comes down or boils down that the automotive industry needs data to make decisions, and with machine learning you can make data-driven decision-making more accessible because you can process more data in a more accessible way. Okay, and I was very unsure about how to go about the automotive stuff, so please, if you have questions or if you want to teach me something, tell me. I want to show 2 things that I'm very excited about that also have to do with machine learning. The first is TensorFlow Quantum, which I started to learn a little bit about a half year ago, and where we use TensorFlow as like the framework from Google that is there for machine learning and deep learning to optimize quantum circuits, because we can look at an angle and optimize the angle in different qubit gates. And the other thing is AlphaFold, which is a really cool thing where we can use machine learning to help us fold shapes of proteins that we could not fold before. So there was this whole questions in chemistry, like how is the body so cool? And the body is very cool because there's DNA in there, and the DNA gets translated into proteins, and each protein has a biocatalyst function, or most proteins have a biocatalyst function. And today the Nobel Prize was awarded for doing catalysts with like biocatalyst functions, and the nature does it all the time, like since ancient times. And now we try to use machine learning to understand how the body makes this biocatalyst, and this is amazing. And at the bottom here is just the amino acid sequence that is part of our calcium channel, which is very interesting, because we often think that our neurons fire just because of electrical impulses, but actually they fire mostly because of ion gradients. So most of our brain is actually not only electric circuits, but it's chemistry. And by understanding and questioning how nature works, with data that we can use in machine learning, we can ask better questions. And I think the most important thing that we can learn from machine learning is that we can have a body that helps us ask new questions. So I hope that someday we will all be better machine learning. At the beginning, it's a start. I'm also still at the start. And I hope that one day we can drive down the roads with machine learning in a safe way, in a predictable way, and in a trusting way. So yeah, if you have questions, please ask. And if you want to teach me something, please teach me more. Yeah.
Alexandra, thank you. It was amazing.
Thanks, Alex. Before we start with the questions, I want to point out that I think we met together 2 years ago, or 3 years ago in 2018. Yep. Back then you have been 17 or 16 years old, and you have talked about machine learning and all of these things. And today you are teaching about quantum computing, still also machine learning, but that's maybe the easier part for you nowadays.
I think actually machine learning becomes the more difficult part, because it's hard to explain something that is machine learning develops all the time, right? So because I'm not into machine learning that much, like, I wasn't machine learning a lot, now I'm more into quantum computing, and that's why when machine learning develops into whole these new directions, this whole dynamic thing, it's hard to keep up sometimes. That's why you need to learn more all the time.
Yeah. But my question actually is like to finish this up. Like, I mean, you have already your bachelor degree from Dublin with distinction, I think. So congratulations to that one. You are now studying molecular biology or
molecular medicine.
Yeah, in Innsbruck. You have been working at MIT and CERN and at some NASA stuff and so on. And the question is just how.
I think I do the stuff that feels fun to me. I'm very bad with like washing the dishes when I'm not motivated because I'd rather take my laptop than wash the dishes. I think the most important part is that I met people that trusted in me and that taught me abilities. And I think the most important thing that I also want to give back to the world is like, sometimes even if you don't understand the things at the beginning, you will understand them at some point. And keep trying, keep exploring things, and keep asking the questions, because there will be people that answer questions. And even if they don't know the answers, maybe you can find some by just trying. I think not fearing to live anymore was a very important part in just trying things out and seeing how far we can go.
Yeah, and how did you develop the passion actually, and when did it start? When did you feel, okay, I want to go into this direction?
It actually started when I was in hospital for some time, and somebody brought me a book with Python, and I started to do Python program while I was in hospital because I could do it in my bed and didn't have anything else to do. And the direction with chemistry started much earlier. I'm very into chemistry because I think it's so interesting how processes come together to build something complex, but at the bottom, they are very simple building blocks. So we have simple building blocks that come together, make something complex, but at the whole surface level, it seems simple again. And this whole building thing is interesting, and there's so much to explore. It's enormous. And this fascination just never left me, this curiosity, I think, yeah.
Okay, so you know what to do the next time when you are in hospital.
I don't recommend it to anybody. Like, libraries are much better learning environments. Libraries are cool. Also, the couch is very cool, because that's the cool thing. I don't need a laboratory anymore if I have a laptop, right? I can just take my laptop and sit down at home. I don't need to go into the laboratory. It's just my laptop.
Yeah, that's cool. So let's start with the questions. I think you have some questions.
Yes, I have a few questions, but I would like to ask first, do we have any questions here in Vienna directly from you? Yes. Just a second.
Thank you for your presentation. So the question from my side would be, okay, you showed us the convolutional neural net, and it's quite easy to train it and to have a decent accuracy. And the point is that it's also quite easy to manipulate the real world data a bit, such that the labels do not match anymore. And what is important, for instance, in the automotive are the guarantees that, okay, imagine I have a network which is trained to recognize the traffic signs, and I have 90% accuracy on my, okay, you have this training data and you have this validation data, and on this data which I haven't seen before, I recognize it with 90% accuracy. And the thing is that, and it was also shown that if you manipulate this traffic sign a bit, you put some in a different lighting conditions, or you put some picture on it, then it's no longer recognized. And what is your thought to it? I mean, how can one achieve some kind of guarantees with this machine learning? Because essentially what you get is a bunch of floats, so the network is like, a matrix of float numbers, and then if it doesn't work, then you have no idea why.
Yeah, exactly. I think that's a very important point. How can we teach them, which data do we need to give the computer so that it best models reality? It's a very important question. Also, when we as humans collect data sets, we often have a bias in there. We pay, as you said, from the same angle, from the same time in the morning, and don't leave out the evening. And we should not fool ourselves with data sets or with accuracy numbers. Better if we have a model that works on noisy data but does a decent thing, then we have a model that works on perfect data that's cleaned up but not anything close to reality anymore, and have some perfect accuracy score. I have not solved the problem how we can make models despite which input we give the excellent output. Because I myself, if you give me some test paper, I will not always score 100%. That's not possible. I believe the most important thing is that we keep exploring different algorithms, that we try to find out when we fail, where we fail, and also where the human errors are in there. And especially in the automotive industry, that we don't go forward with machine learning just because it's machine learning with good accuracy, but we really think about, do we need this algorithm here? Do we need to do machine learning or artificial intelligence? Or are there some things that we can also just hard code with a logic behind it that is unfailable? Yeah. Was this okay? Was this the question, or was it not the answer that you anticipated?
I mean, regarding, I would like to ask you what I thought about how we can achieve some kind of guarantees with this machine learning.
Okay.
Because is it possible, or will it be possible, or is it impossible?
You mean like having 100% accuracy?
I think
or having explainability, because it's often, okay, you have this stuff which is a black box, it works, okay, you give it input, it gives you output, and if you manipulate a bit, then it doesn't work. Then
okay, but I think in terms of explainable AI, we have come a long time, like we have done a few steps and really good progress since I started to look into explainable AI. So for example, when we use AI in chemistry, we really try to figure out like which molecules do work well, which molecules do work bad, and then we go and retest it in laboratory and iterate it over itself. So we, with the help of like real-world experiments, we try to understand also machine learning better in both ways. I think in the automotive industry, what we could do is, I don't think that anything is impossible. I think that we just be a little bit like do the slow progress rather than the fast progress. That would be better. Yeah.
And does it also help to collect a lot of data to be more accurate,
definitely.
right?
Like, I think much more important than collecting a lot of data is collect diverse data and look at where you fail and where you're good at, and then try to improve on where you fail. Yeah.
Yeah. I mean, what we discussed in the morning session, what we found out, and that's very interesting, like, for example, in the automotive industry, when we fill out these captures from Google where you have to say, hey, please mark the boxes with a crosswalk, or the buses or the bicycles or so, they actually use it to train their machine learning models for autonomous driving,
that's
right?
really cool. I also found out that Google actually, like, the part that's actually captured is how you move your mouse. Like, that's the security, not if you get direct pictures. That's very interesting. Yeah, they need data. We need a lot of data. Yeah.
Okay, so we are also working all for Google at some point.
Yeah.
Good. Okay. Any more questions from here, from Vienna?
Yes.
Thank you. So just to reflect on the statement from Seat, in the automotive industry, we need those data, obviously, to train the networks there, especially for autonomous driving. What's your opinion? How important is to get those data, and what are the, let's say, approaches of Google or maybe also some Chinese companies in contradiction to that what we are doing at Europe or in Germany especially? So how to deal with data, how to get it, and how to have some kind of data security and privacy also in behind.
I think what's a really interesting question is, do we only want to work with, for example, pictures, or do we only want to use video data, or do we want to use other sensor data in the automotive industry as well? Because, for example, radar or infrared or any other sensors are also very important data points that we often don't think if we think about car vision. But for the car, it doesn't matter if it's like a like it's a numerical value in the end. It doesn't matter from which sensor it comes from. So we need a lot of different sensor data in my case, in my eyes. The other part is we need, for example, if we take videos, it would be very hard in Europe if you want to blur out all the signs on the cars and all the all the people, because all of the GDPR is, of course, there to protect privacy, but it makes it harder for us to get the data in as fast as possible and as accurate as possible if we have to blur out stuff. Therefore, I think probably people or like companies or countries, they can work more loosely with privacy issues, will be fast in development. On the other hand, I think it's important that the government has put regulations on how we collect data and also how we get privacy at a decent level for everybody, because in the end, if we have a data-driven economy or if we have data-driven decision-making, we want to make the right decisions in an equal way, and not decisions biased towards profit for one company or towards profit for one country or one person. Therefore, I think privacy is important, security is important, and better go slow the correct way than fast in the wrong direction and just destroy yourself in the end. Is it okay? Is it answer?
Fine, thank you.
So, any more questions? Okay, then we can go to the other questions. I have a question from Klaas. Is there a rule or formula? What is the minimum amount of data that you need for a model to be accurate?
It depends. For example, if you do binary classification on an octopus versus a tree, you will need very little data because there will not be so many features that are similar that are very hard to distinct. If you have very similar things that you want with a fine grade level of distinction that you want to separate out, you need a lot of data because then you really need to go more and more into depth into where you can separate the things out in the end. Yeah, so the more like in a decision tree, if you have only one question that you need to ask, you can train it on little data. If you have many questions that you need to ask, many decisions to make, many features to figure out, then you need a lot of data to give the model the time and the input it needs to train itself.
I hope this is a good answer for class. And I have one more from Robert. I saw Android Studio icon on your laptop. So, have you used Google ML Kit in a project? And if so, when could it be useful?
I have not used Google ML tool. I did the Google Cloud Data Engineering exam where I needed to use it, like for practicing, but I haven't put it into a product. And what I used Android Studio most for is for Flutter development, for app development, but just for myself because I like to play around with UI stuff. And yeah. I mean, in the end, it would be very cool if we have, for example, I really like visual context and visual learning. So I think there's a lot of chemistry content missing that is visually presented. So that's why I play around with Android Studio and Flutter to maybe have apps where chemistry is better delivered. Yeah.
Okay, then we have a couple of more questions coming in. So Stanish is asking, how do you go about creating data sets? Kaggle is a database, but where do you collect a customized set?
Okay, I showed one way where you want to collect noisy data. You can go onto Google Image Search, download stuff, and then take out the pictures. Which is, of course, if you don't put out, you should not put the pictures online because there's copyright and everything, and I think privacy is important, right? So don't do that. And the chemistry, for example, for bachelor's thesis stuff, I collected data on molecules, and you can either collect data, of course, in the laboratory, which is often a tedious process, but they're very open data sets from the World Health Organization. There are different chemical databases, and the better the databases, the more expensive the access sometimes gets. So often you need to work together with universities or other parts. But collecting data sets and collecting good data is, of course, a good question. For example, reCAPTCHA try to do it by asking customers. I think I go onto the online and search for datasets. If there are none, I try to combine datasets, and then I try to clean up combined datasets to have a similar format and to contain all the information that I like them to contain. Yeah.
Okay, thanks. Then we have one or two questions about the dystopia that awaits us with AI. So Dario is asking, as a young person, do you think AI is a threat or a useful tool in the future? How to take the fear away from the masses? And also Stanish again is saying, what's the greatest challenge and fear with AI according to you?
The greatest fear and challenge with AI in my case is that we get to a point where we fear to use it because we don't understand it or we are not trained to use it. So running away from something because we don't want to start or because we don't understand is the worst thing that we should do. In my eyes, AI is not a threat. As it's the same like a knife. A knife can be used to make a bread with butter or to kill a person. I think it depends very on how we want to use it and where we want to use it. And therefore, I would say that every person who wants to do good with AI should start as soon as possible so that we have good stuff with AI on the market. But also, I think we often overestimate the power of AI, that they do extremely bad stuff. If we let an AI drive the car, of course, it's our decision that we gave over control. But on the other hand, I think there's also much benefit if we use it in a symbiotic way. So if we humans work together with AI and kind of control each other and help each other. For best example, cancer medicine, AI is much better in predicting cancer and finding diagnosis to cancer than humans are at the moment. So if doctors work together, the AI doesn't have to give medication or do chemotherapy, but the doctors have assistance from the AI to make better decisions on what to do. Yeah.
Okay, cool. Thanks for that answer. And then last question for this session. How do you go about choosing the right AI model? What are the most important things to consider when doing so?
First, what type of data you're working with. For example, I showed the different parts like image data, audio data, or if you use tabular data, those are different things. Then first think if you want to use machine learning, like more statistical, easier to use, and also smaller to train models, or if you want to use neural networks, which are harder, which can abstract data much better in some cases, but are also harder to train and more time intense, need more data. This is the most important part. And then which input they need. So some models need image input or different layers of input. Other models need tabular input. That's the last thing. So the first thing, what do I want to achieve? Then what are the technical requirements? And then what is on the market and fits my solution the best in the smallest and most convenient way possible. Yeah.
Okay,
and what's
thanks.
freely available, of course. Like open source is always better than paying for something. Yeah.
Yeah, that's a good closing word for this session. So, Alex, thank you so much. That was incredible. I think that our someone commented like it was a super intensive and interesting session, but my brain is burning. So I would say thank you very much. Alex is still around here if you have some questions, if you're curious. Yeah, we are going into a short break and coming back together at 3:15 p.m. Central European summertime for the ones who are joining us online. We are going to have a coffee and then go into our last session. So, thanks again.
Thank you, Alexandra.
Thank you.
Have you found your dream job as a developer? Or are you stuck in an unfulfilling job? On WeAreDevelopers.com, you find over 1,000 jobs in Europe that fit the tech stack that you want to work with, and salaries go up to $130K. All you have to do is create a free profile, and you automatically get matched with jobs that fit your requirements. So what are you waiting for? Create your free profile and let companies apply to you now. Have you found your dream job as a developer? Or are you stuck in an unfulfilling job? On WeAreDevelopers.com, you find over 1,000 jobs in Europe that fit the tech stack that you want to work with, and salaries go up to $130K. All you have to do is create a free profile, and you automatically get matched with jobs that fit your requirements. So what are you waiting for? Create your free profile and let companies apply to you now. you found your dream job as a developer? Or are you stuck in an unfulfilling job? On WeAreDevelopers.com, you find over 1,000 jobs in Europe that fit the tech stack that you want to work with, and salaries go up to 130K. All you have to do is create a free profile, and you automatically get matched with jobs that fit your requirements. So what are you waiting for? Create your free profile and let companies apply to you now. And let companies apply to you now. Have you found your dream job as a developer? Or are you stuck in an unfulfilling job? On WeAreDevelopers.com, you find over 1,000 jobs in Europe that fit the tech stack that you want to work with, and salaries go up to 130K. All you have to do is create a free profile, and you automatically get matched with jobs that fit your requirements. So what are you waiting for? Create your free profile and let companies apply to you now. Have you found your dream job as a developer? Or are you stuck in an unfulfilling job? On WeAreDevelopers.com, you find over 1,000 jobs in Europe that fit the tech stack that you want to work with, and salaries go up to 130K. All you have to do is create a free profile, and you automatically get matched with jobs that fit your requirements. So what are you waiting for? Create your free profile and let companies apply to you now. Have you found your dream job as a developer? Or are you stuck in an unfulfilling job? On WeAreDevelopers.com, you find over 1,000 jobs in Europe that fit the tech stack that you want to work with, and salaries go up to 130K. All you have to do is create a free profile, and you automatically get matched with jobs that fit your requirements. So what are you waiting for? Create your free profile and let companies apply to you now. Have you found your dream job as a developer? Or are you stuck in an unfulfilling job? On WeAreDevelopers.com, you find over 1,000 jobs in Europe that fit the tech stack that you want to work with, and salaries go up to 130K. All you have to do is create a free profile, and you automatically get matched with jobs that fit your requirements. So what are you waiting for? Create your free profile and let companies apply to you now. Have you found your dream job as a developer? Or are you stuck in an unfulfilling job? On WeAreDevelopers.com, you find over 1,000 jobs in Europe that fit the tech stack that you want to work with, and salaries go up to 130K. All you have to do is create a free profile, and you automatically get matched with jobs that fit your requirements. So what are you waiting for? Create your free profile and let companies apply to you now. Have you found your dream job as a developer? Or are you stuck in an unfulfilling job? On WeAreDevelopers.com, you find over 1,000 jobs in Europe that fit the tech stack that you want to work with, and salaries go up to 130K. All you have to do is create a free profile, and you automatically get matched with jobs that fit your requirements. So what are you waiting for? Create your free profile and let companies apply to you now. Have you found your dream job as a developer? Or are you stuck in an unfulfilling job? On WeAreDevelopers.com, you find over 1,000 jobs in Europe that fit the tech stack that you want to work with, and salaries go up to 130K. All you have to do is create a free profile, and you automatically get matched with jobs that fit your requirements. So what are you waiting for? Create your free profile and let companies apply to you now. Have you found your dream job as a developer? Or are you stuck in an unfulfilling job? On WeAreDevelopers.com, you find over 1,000 jobs in Europe that fit the tech stack that you want to work with, and salaries go up to 130K. All you have to do is create a free profile, and you automatically get matched with jobs that fit your requirements. So what are you waiting for? Create your free profile and let companies apply to you now. Have you found your dream job as a developer? Or are you stuck in an unfulfilling job? On WeAreDevelopers.com, you find over 1,000 jobs in Europe that fit the tech stack that you want to work with, and salaries go up to 130K. All you have to do is create a free profile, and you automatically get matched with jobs that fit your requirements. So what are you waiting for? Create your free profile and let companies apply to you now. Have you found your dream job as a developer? Or are you stuck in an unfulfilling job? On WeAreDevelopers.com, you find over 1,000 jobs in Europe that fit the tech stack that you want to work with, and salaries go up to 130K. All you have to do is create a free profile, and you automatically get matched with jobs that fit your requirements. So what are you waiting for? Create your free profile and let companies apply to you now. Have you found your dream job as a developer? Or are you stuck in an unfulfilling job? On WeAreDevelopers.com, you find over 1,000 jobs in Europe that fit the tech stack that you want to work with, and salaries go up to $130K. All you have to do is create a free profile, and you automatically get matched with jobs that fit your requirements. So what are you waiting for? Create your free profile and let companies apply to you now.
So, welcome back. We have our last expert talk, and so, Sead, who will it be?
Yeah, so I have the pleasure to invite Michael on stage. He has been working in the Industry 4.0 section for quite a long time. He's a real expert in terms of software architecture, and he will tell us a bit more about why you shouldn't build on a microservices architecture. So please give an applause to Michael.
So, welcome, Michael.
Hello. Welcome. Michael, before you start, what was the motivation behind this topic? Because let's say 10 years ago, we were building monoliths and so on, then we were turning to microservices. And now we are kind of, going away a bit from microservices again, and there is like a big of a flame war outside there. So what was the motivation behind?
Yeah, you're perfectly right. So a few years ago, I would probably have given the talk why you should build a microservice architecture. But there has been a rise in adoption over recent years. So I feel today my topic is much more why you should do something different. And actually my talk is mostly about architectural decisions and how to approach such a decision more than on the particulars of the architecture.
Okay, perfect. So Michael, the stage is yours.
Yes.
And see you later.
Thank you.
Have fun.
Okay. First of all, hello everyone, and I'm really excited to be here. And also really happy about the turnout. So not sure if you see it in the stream, but we have a full house here. And for me, that's the first time in 2 years where I'm actually speaking to real people in presence. So real fun for me. My topic is why you shouldn't build a microservice architecture. But before I set out to give bad architectural advice, I would like to get a little bit of a read of the room. Can you maybe raise your hand if you have, worked on a microservice architecture, built one, interacted with it? Just a bit of familiarity with the topic? Yes? Yes? Okay, I see a strong minority, and I'm sure that everybody in the stream is fervently raising their hands. But for everyone else, I think there's definitely something there for you in the talk anyway, because I will be talking about trees, mostly. So, first of all, before I start with the topic, who am I? Well, I said already, my name is Michael. I'm working for Bosch, and I have been working for Bosch for roughly 8 years, mostly in the field of software development and around that. I'm part of the accelerator, and we are the digitalization unit for powertrain solutions. So Bosch powertrain components are fuel injection system, everything that moves a vehicle forward. And to that end, we are manufacturing parts worldwide, which of course makes a lot of sense. And that is, of course, working a lot with physical products, working a lot with metal. But in 2021, our business is as much about working with data as it actually is to work with physical products. And that's actually where we come in. So at the accelerator, we are building the global data infrastructure that essentially carries our operation in that regard. We have connected more than 1,000 manufacturing lines, which are worldwide. To that end, at the accelerator, we are building and maintaining 7 products, which are real DevOps teams. So all of the teams build and maintain their own product. We are around 40 developers, and these are located in 7 countries. However, the teams are not distributed. We always have a team which has 100% responsibility for the product, and they're usually located close to their customer. One of the countries, obviously, being the beautiful country of Austria, where we have a team that is supporting mainly engineering workflows. So that's who we are, and me personally, I'm responsible for all of the software developers inside the accelerator, which I hope qualifies me to talk a little bit about architecture. So when I prepared this talk, I was thinking a lot about, what would actually give a benefit to you as an audience, and I really feel that we had it already in the moderation. There is a lot of material on architecture, on microservice architecture, and at the end of the day, I would always recommend to read a book instead of, listen to a talk or a 10-minute video if you really want to learn on the architecture. However, what I feel is really relevant, and that is something I think I can add to discussion, is which questions do we actually ask in such an architectural decision, what people should consider, and also how the process works for us. So that's why I also want to start with a short disclaimer. So first of all, as I'm not speaking about facts on the architecture, I'm going to be more talking about my personal experience and opinions. So a lot of what I'm going to say is not, fact-based, and that is, of course, one point. The second one is some of the things I'm going to say is very black and white because I want to get a point across, but reality is often, guided by grayscale and trade-offs. So don't take everything I say too serious. Third one would be, if you disagree, wonderful. So I would love to hear about that, and I will be hanging around after the talk, so feel free to approach me. I love discussing about these topics, and that's also, of course, how we learn. And last but not least, a lot of what I'm going to say is common sense. And I believe common sense is actually one of the most powerful tools in the software architect's tool belt. So let's get started. So I was promising questions. So my first question would be, why should we care about architecture in the first place? And for me, that's actually really easy. We have a lot of good practices in software development, CI/CD, testing strategies, deployment strategies, version control, and of course architecture, and much more. And I believe that all of these serve one purpose and one main purpose only, which is to save time. Because at the end of the day, the saying time is money is very true for our field, because on the one hand, of course, we have the time we invest into building the product. Okay, that's one thing. But also, if we are slower at getting into the market, well, we might lose out on revenue, which is even more expensive. And then also, if we take too long to actually push a product into production, someone else might be first, and we're losing even more money. So it's really important for us that we are fast in these things, and which is also part of why we are called the accelerator. So I believe that the main guiding question for any architectural decision should be, does this help me to get from A to B faster? And of course, it doesn't always have to make you faster right now. There's a lot of scenarios where, get a little bit slower now, but get faster in the long run. For example, talking about something like testing strategies or code quality. That's perfectly fine, but it has to make you faster at some point. And, of course, that's not the whole truth. We had before the talk on security. So at the end of the day, of course, security is a top priority, safety is a top priority. But let's say once we're safe and we are secure, then we first and foremost want to be fast. So that would be the first question about architecture. And the second one would be, what's the right tool for the job? And you probably thought I was kidding when I said I'm going to talk about trees. You were absolutely wrong. I am going to talk about trees. So let's say you have this wonderful tree which is sitting in your garden. And it's a nice day. Everybody's loving the tree, but not quite everyone, because we have two children, and your children just decided that they want to make this lawn their soccer field. So the tree has to go. And you're, of course, tasked with cutting down the tree. So what do? Well, you go to your garage, you pick up your chainsaw, it's a nice Sunday, or maybe Saturday because of the noise, and you cut down the tree. Beautiful day, you do it, it goes quick, it's effortless, and that's actually what we want to feel software development like. Of course, we want to do this quick, we want to feel it effortless. But what happens if a tree is significantly bigger? Maybe it's more than one tree. Maybe these trees are huge. Maybe they're next to a neighbor's house. So suddenly, things get more complicated. If we now try to just pick up the chainsaw and cut down the tree, what we're doing is probably going to be looking something like what this guy is doing. Not an expert on cutting down trees, but to me that looks kind of dangerous and not very safe. And in general, that's, of course, what we want to avoid. So, and also just on a completely unrelated topic, if you feel, if you're pushing something into production, you feel, oh, that is risky, there's probably an issue that you need to address in your overall architecture and setup. But back to the topic. So essentially, if we look at what this guy is doing, we can say, okay, so that might not be ideal. What can we do better? Well, maybe we could bring in some heavy equipment, like a lifter to make it easier to reach the tree branches, or maybe even one of these trucks to just, cut down the whole tree and be done with it. However, if you think about that, pretty quickly, it gets more complicated, because you probably don't own that equipment. No, you have to bring it in. You might have to rent it. Well, then you have to handle the logistics. You have to align with the neighbors. So suddenly, cutting down a tree goes from, we just do it quickly in a day,
to a bigger project. Is this good? Is this bad? Well, I would say it is neither. Because if you have a big tree at your hands, well, you should bring in the heavy tools. On the other hand, if you think of the tree in the first picture, it would be ridiculous to bring in the heavy equipment. And that's exactly what a microservice architecture is in our scenario. So what I want you to be aware of is, if you're building a microservice architecture, you are kind of bringing in the heavy tools. And if you are bringing in the heavy tools, you should actually make sure that you need them. So how do we do that? And I just gathered, that not everybody of you is aware what a microservice architecture is. So I'm just going to cover the basic gist in like 30 seconds. So traditionally, when we were building software, in the good old days, architecture was easy. You had a server, maybe a database, and you were done with your deployment, or maybe you had a few components and nothing too fancy. Today, if you run into an architecture workshop and you look at the wall, it probably looks more like something that belongs into a museum. So the core idea about a microservice architecture is that instead of building an application that does a lot of things, you cut it down into small applications that are self-sustained and that to communicate to each other. There's pros and cons to that, which again I'm not going to cover in depth. But let's look at a few of these, because I'm going to use these to illustrate some examples and to illustrate how we think about these decisions. So again, a list of pros and cons. There's a lot of more pros, a lot more cons. Just a few of those to get going. So one thing that's really great about microservice architectures is it enables good scaling, especially if you only have to scale single components. It's really good and convenient if you work on it with multiple teams. And it's actually very easy to reason about. So if you interact with another team and another software architect and you want to explain what goes where into your product, microservice architectures usually help with that. It also has some cons. So first of all, it's a much more complex architecture, generally speaking, which also makes it expensive. It is more difficult to run because your deployments tend to get more complicated. And in some cases, it requires more discipline to maintain. So you have to be much more diligent about which functionality goes where. You want to take care that the same functionality is not implemented in different ways in different parts of the architecture and things like that. But overall, if you look at the pros and cons of such an architecture, you'll probably see a very long list of pros. And you will see cons, which essentially come down to being only one con. And that con is actually, it's more complex. And most of the cons of that can be derived from that. So it seems to be a very straightforward decision to say, well, just roll with a microservice architecture every time because we have so many pros and so little cons. However, remember what we're trying to do. We want to get from A to B as fast as possible. So complexity is actually the worst thing that can happen to us. And that's, again, where I would say, OK, we know that we have a con which is potentially dangerous, and we have a lot of pros. Well, so next step we should do is actually make sure that the pros apply. So, good scaling. Well, we have good scaling for single components. Well, first question would be, do we even need to scale? So for us, we are building applications oftentimes for internal Bosch users. And you can read on Wikipedia, Bosch has around 400,000 employees all over the world. Well, however, not all of these employees are actually going to be awake at the same time. They are all over the world, so that means roughly a third is awake at the same time. Not every application is actually for everyone. And not everyone is actually going to be using the application at the same time. So concurrent user counts for us are probably in the a few hundreds to a few thousands. So we are never going to scale to millions of users. Well, so obviously, then I do not need to be able to scale to that. And also, if I really need to scale, well, if I'm running a monoserver architecture, I can just deploy 2 servers, slap a load balancer in, and I'm fine. Might be less difficult and is also pretty doable in production. So the important consideration here is, do I actually need to scale individual components? So let's say we're building a web shop and we have, for example, a purchasing module which is really critical to my business. Yes, I want to scale that. If not, well, probably the benefit does not apply. Second benefit, good for multiple teams. Well, do we absolutely need to develop an application with multiple teams? In general, for me, the ideal team setup for building a software product is actually one team. Because, you know, some projects are just too big, you need multiple teams, but multiple teams do always come at a cost. If you have multiple teams working the same product, well, you get an overhead from communication. Things tend to get slower, things get more effort. So we want to get from A to B as fast as possible, right? So that's probably not a good idea. So for us, we actually try to cut all of the projects so small that they can actually be built by one co-located team. So if we don't only have one team, well, that benefit doesn't really apply that much. Easy to reason about. Well, does our application have a lot of interfaces? Are other people relying onto our application? Yeah, then we probably have to reason about it. But if our application is completely insular, we hardly have any interfaces to anyone, benefit doesn't apply. So you can keep doing that, essentially with all of the different advantages such an architecture has. And this leads us to this beautiful decision tree. So, you know, if you have answered basically all the questions with no, and the benefits do not apply, well, then probably you shouldn't build a microservice architecture. And that is, of course, the key point here. If you answer these questions with yes, of course, keep going, and you are probably on the right track. But the important thing here is if the benefits do not apply, well, then you shouldn't do it. Because one thing that's absolutely certain, you might have noticed I didn't talk about the disadvantages. That is because the disadvantages are guaranteed. If you go for that kind of architecture, you will have this overhead. And, you know, team microservices, the guys that have raised the hand, probably know from experience, there's a lot of stuff coming up that you didn't really expect. You know, deployments get more difficult, then you have to worry about monitoring, but hey, we want to consolidate monitoring in one place, so we have to put it in all of the microservices. Where do they even run? How do we keep track of them? And it's just a lot of other stuff that you need to build in the follow-up. That's why I, you know, advise caution to not over-engineer, essentially. So that's the decision tree. So I haven't talked a little bit about why, you know, what you should be thinking about and why maybe not to go for microservice architecture. But I do have a surprise for you. From the 7 products we're building, actually the vast majority is running a microservice architecture. Because especially for the data pipelines we're building, that is actually a very good architectural pattern. So if you absolutely have to go for microservice architecture, I want to give you at least a little bit of advice from our experience that might be working for you. So first of all, I believe that the name microservice architecture is in itself misleading. I would say small service architecture is probably a little bit more fitting. Because one thing I really would advise is don't overdo it. So essentially try to figure out what is actually the lowest amount of different microservices that you can reasonably run and go with that. And just to give you like a number, so for us I would say if you have 3 to 4 microservices per team, you're in a good place. I've literally seen a product that was built by 2 developers, which had 30 individual microservices. It was a beautiful product, it did work well, but you can imagine that it was quite the hassle to figure out, you know, what's running where. If you have 30 microservices, it's even hard to keep in your head what goes into which microservice. So try to split into 3 to 4 microservices per team. In regards to team size, I would recommend to go with the 2 pizza teams. I think that's coined by Amazon. However, I have no idea how Amazon is feeding 8 people on 2 pizzas. So while 4 to 8 people is a very good size for a team, you probably should buy a little bit more pizza. Number 3, which is important to me personally, is do have clear specifications for your APIs. Keep it backwards compatible, or if you make changes, keep supporting the old API. Might not be necessary for your product, but I really believe that it's important to freeze the API specification early in the development process. And also, I can assure you, if you are a few years into production and you keep changing your API, you're not going to be invited to the Christmas party. Next one is about monitoring and deployment infrastructure. So if you are running a microservice architecture and if you are running this in different teams, there's a high likelihood that, you know, every developer has a favorite monitoring tool. So I think you should really take care that you're deploying to only one deployment target, let's say a Kubernetes cluster, and consolidate the monitoring. That is, for us, one of the main priorities, that we actually start to implement monitoring early and consolidate it into one logging and monitoring environment, because microservice architectures are really easy to fix if a microservice actually goes down. But sadly, most of the time, they don't go down. And if they don't go down, good luck finding where the issue is if you don't have consolidated your logging. Second to last, and that's actually the second most important point from my perspective, do not try to implement an architectural solution for an organizational problem. So one thing that I have been seeing is, you have this team, they're probably not working too well together, they're arguing a lot, they're in the same code base, so there's a clever architect coming in who says, well, let's just fix the problem. We are just doing 2 teams, which are each building 1 microservice, and then we're never going to have a problem. I can guarantee you what you're going to achieve is that then they're going to be arguing about their API instead of conflicts into their own code. So yeah, just from my personal experience, it never works to fix an organizational problem with an architectural solution. And the last one, and that's also very clear and dear to my heart, is microservice architectures do not excuse you from writing clean code. So, of course, one of the ideas behind a microservice architecture is, that you decouple, that you have clean interfaces, and to an extent, of course, you force this decoupling because, if it's different services, they need to communicate somehow. However, the logical consequence is not, okay, now we're building microservices, so we can just, put spaghetti code into each microservice and we're going to be fine because, well, we have a microservice architecture that fixes all of that. So again, of course, it still makes a lot of sense to have cleanly organized code, have clean interface specifications, clean data models. And that is also, of course, especially important if you're going with generally bigger microservices like in the first point. So that would be my advice on microservice architecture. And that's essentially all I got on the topic. So I have one last point, which is more about architecture in general and how you can approach that. So let's say this is you. You're building your first architecture. Things are really going well. You've read the books, you've watched the talk, you've done your research, and you're 100% confident that this architecture works and it's great and it cannot be improved. And then you deploy into production. And that's how it goes. Total disaster, servers are burning, customers are screaming, and the coffee maker breaks on top of it. And the one thing I want to tell you is, this is going to happen, and there's nothing you can do about it. So for me personally, there's no such thing as a correct architecture or a right architecture. It's just about, having different degrees of wrong and find a good place in there. And that's also something that's important to me. Again, if we go back to the initial point, we want to get from A to B as fast as possible. If we spend 6 months sitting around thinking about architecture, that's 6 months which we lost and which we're never going to go back in development. So what I really want to encourage you to do is be brave, even if you're not certain about architectural decisions. And also one thing that I believe is very true, the more time you invest into your architecture, the more in love you fall with it, and the more certain you are that you're right. And that much harder it gets to fix it later on. So from my perspective, it is very important to go into production fast and to learn from production. And also, fun fact, for us it's actually no-go to have an architect not working on the solution. Because seeing how it behaves in production, that's actually how you get feedback on your architecture, and that's how you improve in the long run. So that are my 2 cents on microservice architecture. I said it before, I will be hanging around for questions later, so feel free to ask me, and of course, we are going to a question round now. Thank you very much.
Thank you, Michael. This was very interesting. So, and as usual, we will start with the audience. Are there any questions to Michael? Okay.
Just raise your hands, otherwise we start with the questions from the online audience.
Don't be shy.
Yeah, don't be shy.
But okay, we can start with the questions from...
Dennis is asking, isn't the solution a mix of both worlds?
Isn't the solution or?
The general solution, like, isn't it a mix of using, let's say, monoliths and microservices together?
Yes, James was the name, I believe, or right? You're not wrong. You're not wrong. So essentially, I believe by now the decision is not only between monoliths and microservice architecture. Quite the opposite. It's getting more and more grayscale between that, because the big thing coming up at the moment is serverless, which is a very elegant architectural pattern, and also, if you build like really big architectures and really big microservices, the lines are blurring kind of between a big microservice and a monolith. But I think the key differentiating factor between something you would consider a monolith and consider a microservice is actually about this segregation of functionality inside of the same product, and essentially having two products that run to serve the same customer need.
Mm-hmm. Okay, thanks. Then Klaas is asking, are there use cases where you say only a microservice architecture makes sense for this specific product, solution, whatever?
Yeah, I would actually be very hesitant to say there are certain use cases which 100% you have to build a microservice architecture. And there are certainly specific use cases that really lend themselves to that. So one good example is actually the kind of data pipelines we're building, where you have a lot of components where you really need that fine-grained control about what to scale, what not to scale. So very specifically, if you have to scale in certain components but maybe not in others, it's really important to optimize costs. And also, if we're looking like, for example, big internet pages with a lot of different functionality that sees strongly varying degrees of use. So you might have, I don't know, a site like Amazon where you have very heavily used modules like search and something like that, and maybe less used modules. That also makes a lot of sense.
Okay. Quite a tricky question from Clock29. In terms of architecture, is there something more than these two options, like the big systems, monoliths, and microservices? Like, is there something in the future or so, how you would make a different architecture in general?
Yeah, so personally I believe there's actually 1 million different architectures. It's more like, boxes we tend to put them in. And for every architecture we're looking at, we essentially try to put it into a box. And those are, of course, two of the boxes. We said monolith, microservice architecture, serverless is a new box we're using for that. But then again, of course, there's a lot of variation between these, a lot of mixing forms for that. And I think at the end of the day, architecture is just, a language we speak to essentially make sure that in the team we're actually talking about the right thing. And it's more means of, of communication than a technical thing, because that's how we think about what we're doing, what goes where. And, whatever means to facilitate this communication actually works.
Yeah, I mean, you mentioned it just right now. Gottfried is asking, what's your opinion on serverless?
I love it. So in general, serverless has a lot of very strong advantages. Overall, you have this flexibility. If you do not see a lot of use, you essentially don't pay any money. If you see a lot of use, it gets expensive, which is really great from a business perspective, because, if you have more use, you probably earn more money and you can afford it.
It's a luxury problem then.
Exactly. The only thing where I would say serverless is something where you have to consider really hard is also at the same level of load. Serverless architectures tend to be a bit more expensive. And also you have to put in additional efforts to engineer to cost in a serverless architecture. But then again, you can maybe start serverless and switch over later. So that's definitely also an option.
Okay, that was already the last question. I think the key takeaway from this session is actually that you, not just in software architecture, but in general, need to think about you want to go from A to B and to have some solution for a problem. And it's not about building complex and best technologies and software and so on, but to actually solve the solution, right?
Yes, absolutely.
Good. Then I would say thank you, Michael.
Thank you.
Very interesting.
Thank you.
And yeah, that was our last session, right, Josie?
Yes, it was the last session. Thank you, Michael. But it's not over.
Yeah.
Not really for our people here in Vienna. So we will have now our DJ Andreas, as mentioned already. We have some food, we have some drinks, and especially we have also our colleagues Felix and Klaus. They brought their daily work with them. So if you can see big SUVs at the back, this is their daily work. So you can grab a look inside what they are doing, ask them a lot of questions, and get in touch with them. So.
Okay, yeah, with that said, I just want to say to the online audience, thank you very much for joining us again. This was one hybrid edition of WeAreDevelopers Live. Finally, after 1.5 or almost 2 years, again, a physical event. We have a full house here. That's very cool to see these people. And for the online audience, we will meet each other again in a couple of days with our machine learning day. So stay tuned and yeah, watch us again in a couple of days. And with that, I would like to say bye-bye to the online audience.
Thank you.
So, and for the ones here in attendance, yeah, let's grab the food and drinks and coffee, and let's see what is there in the cars. And yeah, that's it.
Thank you.
So, thank you very much.
Look, Sean. Our goal is for all Bosch locations worldwide to become CO2 neutral. That's why we thought we should team you up with, well, someone who truly represents the future. The future. The future.
Now's my time. You're about to win.
Well, bring it on, little one.
My first beat. Pump the heat. Save energy. Works for me.
Okay, cool. Drilling tool. Super strong. Last so long.
Whatever. I mean, it's clever. But back to me. Charge and eat. Electric drive. My cool lights. I drop the mic.
I like your bike.
Hey!
Take steps with me. Save energy. Water saving camel saying, how amazing. It's time to quit. That was fun. It's past your bedtime and I'm done. Like a Bosch. Like a Bosch.
Stop the battle, let's unite. Carbon neutral, that's how we fight. Cause time is running, we need to act. Can do so much, that's a fact.
Okay.
E-bikes, heat pumps, Bosch's tools. Basic stuff you learn in school.
Dang.
Mountain ices, climate crisis, smart devices, awareness rises. All I'm saying is stop delaying, work together, I ain't playing. Every little choice can make a change. Hand in hand for a new wage.
Truly represents the future.
So many ways for better days. So many ways for better days.
That was so fun.
This works.
Live sustainable, like a Bosch, with many eco-friendly solutions for a better future. Because every little choice can make a big difference. That's Bosch.